Now let's transition from our two-way merge sort to a more general and more efficient external merge sort. The basic idea here is to make better use of the B buffers of memory that we have been given. When B is bigger than 3, how can we utilize them? Well, in pass 0, we'll be working on much bigger batches, and in pass 1, we are going to merge many streams together at the same time. So let's see how that works. To sort a file with n pages using B buffer pages, in pass 0, we will use B buffer pages at a time. So we read in B pages from the input disk, we run quicksort on that buffer in memory to generate a run, and we write that run to the sorted output back to the disk. The run is B blocks long, so at the end of doing that to the entire input file, we will have n over B ceiling of sorted runs, each of which is going to be B pages long, except for the last one, which might be a little bit shorter than B. Now in pass 1 through n, we will merge B-1 runs at a time using B-1 buffers in memory for inputs, and 1 buffer for the output. The basic idea in pass 1 is we load the first page of each of the B-1 runs into memory, so each memory buffer for input here shown in maroon is associated with a different run. Then we take the lowest value on any one of those buffer pages and remove it to an output buffer. We keep doing that until the output buffer is full and we write it back to the disk. If one of these input buffers is empty, we read another page from its constituent run. So we are streaming these input pages through these buffers to the output, and we do this for B-1 buffers at a time. Since each one of these runs was B pages long from our previous pass, the sorted runs at the end of pass 1 will be of length B times B-1, since we have merged B-1 at a time during this pass. So let's analyze the cost of this general external merge sort algorithm. First, the number of passes that this algorithm is going to take is this. How does this work? Well, we get 1 for pass 0, but then how many subsequent passes do we actually need? Well, at the end of pass 0, we generated n divided by B ceiling of runs, each of which is of length B, except perhaps for the final run, as I said earlier. In each of the subsequent passes, we merge B-1 of these runs. So how many passes do we need to go through all those runs? Well, it's going to be log base B-1 of the number of runs. And we take the ceiling of that number in case it is actually not a multiple of B-1. Now, as the cost per pass is still 2n, since we read the file and we write the file on every single pass, so the total cost in terms of IOs is going to be 2n times the number of passes, which is shown here on the slide. So to give you a concrete numbers, think about the following. Suppose we have 5 buffer pages and needing to sort a 108-page file. In pass 0, we'll take that 108-page file and write out 22 sorted runs of 5 pages each. So that's 108 divided by 5 ceiling. The last one is going to be 3 pages because we don't have a multiple of 5 here. In pass 1, we take those 22 sorted runs and we merge 4 of them at a time together using our last one buffer page for output. So that is going to generate 22 divided by 4 ceiling, which equals to 6 runs. Each of those runs is going to be of 20 pages long because we took 5-page runs from pass 0 and we merged them together 4 at a time now. The last page, again, won't be quite long enough. It will only have 8 pages because we had some leftovers in pass 2. We merge together those 20-page runs and we get 2 sorted runs, one of 80 pages and one that is smaller, only 28 pages. And in pass 3, we realized we are done at that point. So at that point, we have a sorted file of 108 pages. So just to check with the formula that I was mentioning earlier, this should be according to the top of the slide. 1 plus the ceiling of log base 4 of 22, which equals 1 plus 3, which equals to 4. So this basically works out. I want to emphasize, however, that in this class it is important for you not just to memorize the cost formula that we show on these slides, but also to understand how they are actually derived. Our goal here is actually to teach you the concepts such that you'll be able to derive other kinds of cost formulas for different situations. So, more generally, let's look at the number of passes of external sort for different sizes of n and different numbers of buffers. Look at the bottom of this chart. For a billion-page file, if we have 257 buffers, we can actually sort the entire file in only 4 passes of external merge sort. Now, this is the sort of algorithm that has logarithmic benefits that we also saw earlier when we were talking about B-tree search. We can take very, very, very big files, and because we are taking the log with a high fanout, in this case b-1, we are getting very nice reduction in the amount of I/O work that we actually need to do. And in this case, that corresponds to the number of passes that we need to take in order to do a sort. It's often common to figure out how much memory we need to actually sort a file efficiently. So one reasonable question to ask is, how much data can we actually sort in just 2 passes, namely pass 0 and 1 pass of pass 1? So let's analyze that. Each sorted run after phase 0 or pass 0 is at most of size b, with the last one being a little bit shorter potentially. Now we can merge up to b-1 of those sorted runs in phase 1. So the total file size that we can merge is b times b-1. If you look at that, that's just about b squared, a little bit off, but close enough. So we could say, as a rule of thumb, that you can sort X amount of data in about square root of that amount of RAM, or main memory. That's quite a nice ratio. If you have to sort really big files, you only need a square root amount of the memory in RAM, as we saw on the previous slide.